We now start the discussion on module number 1 of chapter 7. In this module and particularly in this chapter, we are going to discuss some special kinds of functions from real analysis, namely functions of bounded variations and absolutely continuous functions. We start the module 1 with functions of bounded variations. Now, you can ask why we need to know about these functions, because in the last two chapters, that is in chapters 5 and 6, we have defined a new integration process, namely Lebesgue integration. We have seen which functions are Lebesgue integrable and for which functions Lebesgue integral exists. We have established many important results of Lebesgue integration, but ultimately we are going to prove the fundamental theorem of integral calculus for Lebesgue integration. And in order to prove that particular theorem, we need the concept of functions of bounded variation. So, let us go to the first slide to see the formal definition of a function of a bounded variation. We start with the formal definition of a function of bounded variation. Definition 1. Let f be a function defined on closed interval a b. We take a partition P, a is equal to x0 less than x1 less than x2 less than xn equal to b of closed interval a b. Consider this sum, which we call VPF. It is defined as sigma I is equal to 1 to n mod f x I minus f x I minus 1. This is called the variation of the function corresponding to the partition P. We take the supremum of VPF, where the supremum is taken over all possible partitions P of closed interval a b. If the supremum is less than infinity, then f is called a function of bounded variation on closed interval a b. And this number supremum P VPF is called the total variation of f on closed interval a b, and it is denoted by this symbol VABF. Now, the first question arises that why the term bounded is in the name of the function. First observation is that every function of bounded variation must be a bounded function on closed interval a b. It is quite easy to prove, because if I take any x belonging to closed a b, see that a x b, if we call this partition P0, then P0 is a partition of closed interval a b. And obviously, if we consider mod f x, then mod f x is less or equal to mod f a plus mod f x minus f a, and this is less or equal to mod f a plus VABF, the total variation. and since the right hand side is a constant and this is true for all x belonging to closed interval a b, this shows that a function of bounded variation must be a bounded function. The next question is whether the converse is true. We will show that the converse is not true. So, in other words, we will give an example of a function which is bounded, but is not a function of bounded variation. Let us consider the function f defined on closed interval 0 1, where f x equal to sin 1 by x when x is not equal to 0 and equal to 0 when x is equal to 0. Observe that this function f is obviously bounded. Now, consider a partition p k in this way. The first point is 0, the second point is 2 by 2k plus 1 pi, then 2 by 2k minus 1 pi, etc., etc., then 2 by 3 pi, 2 by pi and 1. So, this is a partition of closed interval 0 1. If we consider the variation of the function corresponding to this partition, it is quite easy to see that V p k f is greater or equal to 2k, which means that if we take more and more points in the partition in this particular manner, then the variation becomes large and large. So, V 0 to 1 f, that is the total variation of f, must be equal to infinity. So, sin 1 by x is a bounded function which is not a function of bounded variation. Now, consider another aspect of function of bounded variations. We want to examine its relationship with the notion of continuity. Why? Because see that if f is a function of bounded variation on closed interval a b, then it is bounded in closed interval a b. And you all know that if a function is continuous on closed interval a b, then also it is bounded on closed interval a b. So, both continuity and being a function of bounded variation are stronger properties than the property of boundedness when we are considering a function on closed interval a b. So, first we show that there is a function which is continuous, but not a function of bounded variation. Take the function f x as f x equal to x cos pi by x when 0 less than x less or equal to 1 and takes the value 0 at x equal to 0. You know that this function is continuous in the whole interval closed 0 1. Now, take the partition P consisting of the points 0, 1 by 2n, 1 by 2n minus 1 dot dot dot, 1 by 3, 1 by 2 and finally 1. if we consider the variation of the function corresponding to this partition, then this is equal to mod f1 minus f half plus mod f half minus f1 third plus mod f 1 by 2n minus f 1 by 2n minus 1 plus mod f 0 minus f 1 by 2n, and this is equal to mod 0 plus half plus mod 0 plus half. Then I have two terms equal to 1 by 4, and in this way I have the whole sum is equal to 1 plus half plus 1/3 plus 1 by n, which is the nth partial sum of the harmonic series sigma 1 by n. Now, you know from the theory of infinite series that this harmonic series is divergent to plus infinity. So, this shows that if we increase the number of points in the partition P in this particular manner, then VPF tends to infinity as n tends to infinity. And so, this particular function f, though is continuous, is not a function of bounded variation. So, what we were establishing, see that sigma 1 is equal to 1 to infinity, 1 by n is infinity. So, supremum over P VPF is equal to infinity, and so f is not a function of bounded variation. Now, consider the other picture. We can show very easily that a monotonic function is a function of bounded variation. We will come to that result later also, and with the help of that observation, we can say that every step function is also a function of bounded variation, but see that step functions can have finite number of discontinuities. So, a function of bounded variation need not be continuous on the whole interval. Now, we prove another result, lemma 1. First, if f is a function of bounded variation on closed interval a b, then it is also a function of bounded variation on any sub interval of closed interval a b. Conversely, if a less than c less than b and f is a function of bounded variation on both the sub intervals closed AC and closed CB, then it is also a function of bounded variation on the whole interval closed AB, and moreover we have VABF equal to VACF plus VCBF, that is the total variation of f for the whole interval AB can be obtained as the sum of the total variations of f corresponding to the two sub intervals. Of course, we can extend this result to finite number of sub intervals. Let us see the proof. Let closed interval CD subset of closed interval AB. We start with a partition P1 C equal to x0 less than x1 less than xn equal to D, which is a partition of closed interval CD. Now, see that if we take the union of P1 with the 2-point set AB and write it as P, then P is a partition of closed interval AB and VP1F is less or equal to VPF, which is less or equal to VABF, the total variation of F, and which is already finite. Since this is true for any partition P1 of CD, so it follows that F is also a function of bounded variation on CD. Now, for the converse part, let A less than C less than B and F is assumed to be a function of bounded variation on both the subintervals AC and CB. Now, take a partition P of closed interval AC and take a partition Q of closed interval CB. Now, see that P union Q is a partition of the whole interval closed interval AB, and from the definition of variation of function, how we defined it, it readily follows that VPF plus VQF is equal to VP union QF. But see that VPF plus VQF is equal to VP union QF. This is less or equal to VABF, the total variation of F corresponding to the whole interval AB. Now, since F is assumed to be a function of bounded variation on AB, so the right hand side is a fixed number. The partitions P and Q are independent of each other. So, if we now take supremum over P and then we take supremum over Q, we have VACF plus VCBF is less or equal to VABF. Now, let F be a function of bounded variation on both closed interval AC and CB. We start with a partition R, A is equal to x0 less than x1 less than xn equal to b of closed interval AB. Now, see that the point C may be a point of this partition or may not be a point of this partition. Without any loss of generality, let us assume that C is a point of this partition, say C is equal to XR. Then observe that the points from A to XR forms a partition R1 of the interval AC, and the points from XR to B form a partition R2 of the interval CB, and obviously R is equal to R1 union R2. So, here R1 is A equal to x0 less than x1 less than xr equal to C, and R2 is C equal to xr less than xr plus 1 less than xn equal to B, which are partitions of AC and CB. Of course, again from the definition of variation, it follows that VRF is equal to VR1F plus VR2F. This is less or equal to the total variation of F for the interval AC plus total variation of F for the interval CB. Now, the right hand side is a fixed number and since this is true for all partitions of AB containing the point C, and the variation does not decrease when we insert a point in a partition, therefore, it readily follows that VABF is less or equal to VACF plus VCBF, and we have the observation that f is a function of bounded variation on closed interval AB, and using the two inequalities we have the equality VABF equal to VACF plus VCBF. We have already told you that every monotonic function is a function of bounded variation. Again, the proof is very simple. Next, we prove a very important result which gives us a characterization of the function of bounded variation. The result states that a function f is a function of bounded variation on closed interval AB if and only if it can be expressed as the difference of two monotonically increasing functions. First, observe that obviously the condition is sufficient, because we already know that monotonic functions are functions of bounded variations. So, if we can write f equal to say phi minus psi, where phi and psi are monotonically increasing functions, then phi and psi are functions of bounded variations, and we know that difference of two functions of bounded variations is also a function of bounded variation. So, the condition is obviously sufficient. We will now prove that the condition is also necessary. So, suppose that f is a function of bounded variation. Take pi x as the variation a to x f and psi x as pi x minus f x for all x belonging to closed interval a b. See that for x equal to a, we have pi a equal to 0. Observe that if we take two points x and y from closed interval a b, where x is less than y, then pi y minus pi x is equal to v a to y f minus v a to x f. This is equal to v x to y f, and this is always greater or equal to 0, because the variation is always non-negative, and this shows that x less than y implies pi x is less or equal to pi y. Similarly, we can also show that x less than y implies psi x is also less or equal to psi y, and this shows that both pi and psi are monotonically increasing functions. So, f can be expressed as the difference of two monotonically increasing functions. We have also established in the course, the details are not given in the presentation, that if we take a Lipschitz function, then these Lipschitz functions are also functions of bounded variation. Similarly, if we take functions which have bounded derivatives, then these functions are also functions of bounded variations. So, there are many examples of functions of bounded variations, and now if we try to understand which functions are not functions of bounded variation, just recall that the function f x equal to sin 1 by x or f x equal to x cos pi by x, these types of functions are not functions of bounded variation. In general, a function f is a function of bounded variation if it has finite curve length on closed interval a b. And so, a function which have infinite curve length in a finite interval is not a function of bounded variation. So, to summarize, what we did in the first module is that we have defined some special types of real functions, functions of bounded variations, and we have seen its properties, and most importantly we have found a characterization of the function of bounded variations, that a function of bounded variation can be expressed as the difference of two monotonically increasing functions, and this particular characterization will be of much help later in this chapter as also in the later chapters. And we finish this module